Hello, I'm Konstantinos Hadligerudis, one of the associate co-chairs of the TC, and it's with great pleasure that we are hosting today Ludovic Righetti, and I will try to do a very short biography. So Ludovic is an associate professor in the electrical and computer engineering department of the New York University, and he got his engineering diploma from EPFL, and he was also postdoc in many good labs, and also a group leader in Max Planck Institute of Intelligent Systems, and also a receiver of many awards and a lot of nice work. So it's with great honor and pleasure that we are hosting him. And please, Ludovic, the floor is yours. And thank you for coming.
All right. Yeah. Hi, everyone. Thank you so much for inviting me. Maybe full disclosure, since it's a talk in the TC on a model-based optimization, I'm going to go quite technical on certain things. Yeah, I hope it's okay. I thought that's the only occasion I have to show certain things. So yeah. So before I start, I'd like to this is the work of the students and postdocs in my lab. So they deserve all the credit if you like anything you see. So yeah, so maybe before I start, let's just make sure we speak about the same thing. So I'd like to start with a quick introduction of what I think is state of the art in movement generation. That's not everything, but it's certain things. And what do certain things mean? And then we will see how I use these ideas to do model predictive control, and then to start to basically include learning into what we want to do. So model predictive control, right, is this notion that you do things online, and at every instant of time you measure your state or the state of the environment, and from that you optimize a trajectory based on a model that you have, and it tells you what you would like to do, and then you execute the first command, and obviously your model is not the world, so you get something slightly different. And then you remeasure what you are and you re-optimize, right? And this optimization, this idea is that as you do things online, you have a feedback controller that is an optimizer that actually gives you the optimal thing to do at every instant of time, and corrects for any mismatch between what your model is and what the world is. If you take reinforcement learning, a lot of methods based on learning, the idea is that you're not going to compute anything online, but you're going to pre-compute a policy, pi of x, that will map for any possible state, any possible measurements that you have, a control action. So the idea is that there's nothing done online. All the compute that you do is done offline. But the idea is that you do the exact same thing, right? You use the same model or similar models, and you want to optimize certain performance cost. Either you want to minimize or maximize, but that's the same thing. If you take the two extreme views, right? One extreme is that you will take explicit dynamics, so like rigid body dynamics typically, or some linearized model for MPC. And for the most extreme in RL, you will take a simulator and you will pretend that this is not a model and you don't know anything about it. But at the end, it's a simulator that is also based on the same dynamics and use exactly the same equations that you use in MPC, right? And usually you basically formulate these problems, you derive algorithms in between those things by basically formulating numerical optimization problems that you try to solve efficiently. Maybe one of the things that is nice when you do things online is that you have a trajectory optimization problem, so you don't have to compute a policy in the sense that you don't have to compute a mapping from every state to any control, but you just compute something for one given state, right, which is your initial condition. You have guaranteed of convergence if you do things well. You compute things in real time, right? And you can guarantee satisfaction of constraints. The problem if you do that is that you can get stuck in local minimums. It's very difficult to deal with discontinuous dynamics, especially because of the type of algorithm that you use to do MPC. And it's very hard, actually. Maybe that's the biggest problem in MPC, is that we don't know how to include sensing really well. So how do you include vision? How do you include force sensing? How do you include all the things you would like to use in your state space model? It's not something that is very well discussed. So I'll show a few ideas on how you could do that. When you do RL or maybe other things, you want to basically do a policy optimization. So globally, you want to find a global policy, which is really a function, it's not a trajectory, right? You can deal with discontinuities if you use the sampling-based methods, right? So you don't care about taking derivatives. And one of the, I think the big strength, right, in R is that you can use multimodal sensing. So you can really nicely, there's a really nice way to include vision and other types of sensing, which I think struggle with the way we tend to formulate MPC these days. The problem though is that you have no guarantee that things will converge. We don't really explicitly use model. We assume we have black box and we just sample from it, but we pretend we don't know the model. And it's difficult to transfer to robots. So doing MPC, in my experience, is actually there's no problem transferring to robots. It just works, even if your model is not very good. And you don't have guarantee that you can satisfy constraints typically when you use a functional approximator, it is a neural net, right? And both problems, they have an issue, which is finding good cross function. There's a third way to generate movement, which is learning by demonstration, that is becoming, or learning by imitation, right? Which is becoming really big right now in manipulation. But here I'm not talking about it because there's no notion of reasoning. It's really you just repeat what you've been demonstrated, but there's no notion of computation or reasoning that is done either online or offline to actually decide what you do. But this is interesting. So in my work over the work on my lab over the past few years, we spent a lot of time designing custom solvers to MPC, and so and then we've managed to basically run nonlinear MPC, so solving the full using the full dynamics of the robot, full rigid body dynamics, online at a very high rate. So here's an example at 1 kilohertz. You can actually run those things. So here this is based on a not R solver, but a solver called Crocodile, which is was developed by Carlos Mastali and Nicolas Mansa, which you see here. And what is nice when you do things online, right, is that you can on the fly recompute trajectories. So for example, the robot can decide to go one way or the other depending on its state. So you don't have to pre-compute those things. This is done on the fly as the robot moves and interacts with the environment. And still you remain very precise, so you can really achieve the task and do things like that. So I think that's quite interesting. The other thing, so we designed some custom solver for leg robots, so you can get robots to do you can ask, well, you can robots to get to walk, to trot, and things like that. But what you can do is you can do anything, right? So you can ask the robot to reach a certain height, and on the fly you can generate dynamically consistent trajectory. You can execute on the fly on the robot, and you can do arbitrary movement, which is kind of nice. One of the big problem, and that's where we'd like to show you some more maybe technical things, that when we do those things right now, MPC and most of the solvers are based on some sort of differential dynamic programming approach or iterative LQR. And it's not really clear how you add constraints to nonlinear MPC so you can still do things online, right? We know how to solve optimization problem with constraints, but we don't know how to do that online really well if the problem is nonlinear. And so we started to look into that kind of by chance, I would say. And so the thing we realized is that we keep inventing new optimization algorithm, and I include myself in that. We say, oh, we need special algorithm for robotics because we're special. We're not like everyone else. And then we basically our community use and abuse DDP-like algorithms by saying, well, DDP is really fast because we have a linear time complexity. Well, there's a linear complexity in the time horizon, so it's a really nice way to do optimization. Except that when we do that, we don't associate that to actually let's say textbook optimization algorithm. So then we cannot tap into this whole literature and do things. So one of the questions that I didn't ask, but that the students in my lab asked, because I kept telling them, yeah, DDP is like SQP, is the same thing, don't worry. They actually didn't believe me, and they started to look into the details, and they said, so why don't we use just the textbook? So I don't know, my reference textbook for optimization is the book of Nocedal and Wright. So why don't you just take chapter whatever 5, 6 and just implement what they say? And why would that be better than the things we do as roboticists? We are not people who do numerical optimization, right? And so basically we started to reinvent things that were already invented many years ago. So let me explain you why and what happened. And here, maybe it's obvious to people, but we haven't found this in the literature in robotics. We have found that in the literature in control, and somehow I think it has been ignored or not unknown in our community. And so I think I talked with a few people that we all have kind of rediscovered something that actually was known. And so the thing that I realized is that we kind of rediscovered is that doing LQR, as in iterative LQR, right, is nothing else than just doing a smart Gaussian elimination in a matrix with a certain structure. And once you understand that, basically, we realize that there's no need to do any of the algorithms. We reinvent any of these DDP-like algorithms that we've been developing over these past few years. So let's start very simple. Let's start with a simple problem, a quadratic program, a quadratic cost with linear dynamics, right? So it's a linear quadratic problem. So the solution of that, right, you can solve it in two ways. One way, you can write this as an optimization problem given to a QP solver. There's only equality constraints, right? You can even solve it explicitly. But you can give it to your solver, and then it will give you a trajectory of states and control, and this is what you should do, right? Or you can do LQR using the Righetti equations, right? And then what you get is not a trajectory, but you get a control law that maps every control, every possible state times k gives you the control that you need to do, right? So it's a global policy that you can use for anything. So you don't have to recompute things. And seemingly, if you just look at the way I explained that, this seems to be two different methods, right? This seems to be two different methods to solve the same problem. And so one question is that, are they really different? What's the difference between these two things, right? If I do trajectory optimization, so it gives this to a QP solver that gives me a solution, what does it actually do? And how is it different than using Righetti equations to do LQR? And is there an advantage of using one versus the other? And so if it's obvious for everyone, well, I apologize. It's just because I was really ignorant on that. But I think maybe it's not for many roboticists. So let's look at the trajectory optimization problem. Let's assume I want to solve the QP. So basically what I will do is that I will write the KKT conditions, right? The first order conditions of optimality. And so you write the Lagrangian of the problem, which is the cost plus the Lagrange multipliers times your constraints, right? We have equality constraints, and the KKT condition just says that the partial derivatives of the Lagrangian with respect to the control of the states and the Lagrange multiplier should be equal to 0, right? And so you write this, so the conditions, they look like that for the problem I wrote. So don't look at the details, it doesn't really matter. My unknown or the control use the states x and the Lagrange multipliers lambdas, right? And I order them in time from 0 to n. But if you look at that, right, so you have a big matrix times some unknown is equal to something. And so the solution is that if you invert k, right, in some way you find y, and that's the solution to, that's what your QP does, right? It finds y, and that's the solution to the problem. So if you look at the structure of this thing, you see that you have blocks. So actually you have blocks on the diagonals, and then you have blocks on the side of the diagonal. So you have a three-diagonal structure for the matrix. So I'm going to call that G and M, and everywhere else you have zeros, right? So if you want to invert this matrix or solve this equation, you can do some sort of smart Gaussian elimination. So, and then I'm going to call y the unknowns, right? Y for every set of time. So the solution, right, is doing the inverse k minus 1 times g is equal to y. That's the solution to your problem. That's the solution to trajectory optimization. And the question is that how is it different from doing LQR? And that's I think interesting. So if you look at, so that's again rewrite the matrix. I got rid of the zeros. I just put the blocks. What you can do is you can do Gaussian elimination, right? To solve this problem. And if you do it smart, you might be able to do that well. And so since the KKT matrix is three-diagonal, it turns out that there's a lot of people who looked at this problem outside of robotics, and there's a lot of algorithms to actually solve problems that look like that. There's actually algorithms that are even log of n complexity if you parallelize. So actually it's faster than the kind of things that we do when we do LQR. So let's look into the details. So I can start solving by the last row, right? So the last row, I can just say y is equal to g minus 1 times etc. Right? So I can write this equation. It's not so interesting to see the details, but I can start solving from the bottom, and then I can solve the second to last row, and I get something. And then if I keep doing that, I can go up all the way up. And then I get what I call the backward sweep, right? So I start from the back. I solve. So what I will solve is I will solve for what I call G bar, which is a bunch of matrices like that. And can you see my cursor when I move?
Yep.
Yeah, okay. And then you can do a forward solve by feeding the initial conditions of your problem, and then you can solve for every. So the y's will be your trajectories, your Lagrange multipliers, right? And you use state and control trajectories. And so that's one way to solve the problem. And then say, okay, this is kind of a recursion that looks like the backward and forward sweep, right? So if you go into the details, and here I just write down the equation so you can do it, but it's not interesting to look at the details. If I write this J bar, it looks like that. So there's R, which is my cost, right? B, which is the control to state mapping, and P is going to be the value function actually of the problem. And if I can invert that explicitly, so the inverse looks like that. It's a bit ugly, but it doesn't matter. But if you look at what these terms H and P mean, they look like these two things, and this should remind you Riccati equations, right? So basically, when I do Gaussian elimination, what I have is that I have recursive equations that start to look like Riccati equations. And actually, if I solve exactly for y, right, because I said the forward sweep gives me y, so the y is x, u, and so the control, the state, the control, and the Lagrange multipliers. If I actually write this down, what I will see is that the control looks like that. And so basically, the control is LQR. So here's and I can recover the Lagrange multipliers by multiplying the states by the value, right? The cost to go. Basically the thing that is well, it was not obvious to me, but is obvious to a lot of people outside of robotics. The backward pass of LQR is just one step of that's a backward sweep of Gaussian elimination, of a smart Gaussian elimination that is called Thomas algorithm. So basically means that every time we do any LQR type thing, what we're really doing is a fancy Gaussian elimination. And so then when we do DDP and LQR type of things, what we're really doing is a numerical trick to invert smart Riccati matrix that is straight diagonal. And so then we can just tap into all the optimization literature without having to invent something new. So let me show what are the consequences of that. So if you write down that's now a nonlinear problem, that looks like that, right? So an arbitrary cost, arbitrary dynamics, but no inequality constraints, right? A DDP-like algorithm goes this way. You would take a quadratic approximation of your cost. You would take a linear approximation of your dynamics. Then you will do LQR, right? By just solving your Riccati equations. Then what you will do, and that's maybe the weird thing here, is you would say, oh, I'm going to integrate the dynamics non-linearly. So I'm going to do line search, and by doing that, I'm going to evaluate the cost for different steps of my updates for my control. And I'm going to roll out the dynamics non-linearly. And then I'm going to, when I found a good update, right, I will update my control and my states, and I will start again. So that's the loop, or any of the probably hundreds of DDP-like algorithms that have been published in robotics, right, these past few years. And there's a lot of variations of that. If you do an SQP, so like you open the Nocedal book, right, and you take, I don't remember the chapter, but you just implement what they say. What you do is you take a quadratic approximation of your cost. That's the same thing. Then you take a linear approximation of your constraints, right, which is the dynamics, which is what we do in DDP. And then you will solve a QP that corresponds to these approximations, right? And so that here you say, yeah, but that's not the same, right? If I do LQR, if I solve my QP, that's not the same. Well, actually, I just showed you that's the same thing. If you solve your QP using the three-diagonal structure of the Riccati matrix, so you just smartly solve your problem, then you get the linear complexity in the number of steps, right, in N. And basically what you do is you literally do LQR if you've implemented your numerical optimization properly, right? So you do the same thing. So now the only thing that is actually different, if you just apply a textbook thing, is that in a normal textbook thing, you don't do nonlinear rollout. You do a linear update because you're in a linear model. You do line search using that, and then you will find an update. So that might actually violate your constraints, your equality constraints. So when you do that, you have no guarantee that the dynamics will be satisfied. So now you need to find a merit function that will try to trade off between constraint satisfaction and improvement of cost. But this is well known, right? People have been doing that for 40 years in optimization. So that's the big thing. Here we don't do, but that's another thing here. When you do a nonlinear rollout in DDP, the moment you do that, you lose the guarantee that you have a descent direction. So you don't know if you actually have a descent direction. So you lose actually you lose some of the convergence properties of your algorithm. When if you don't do a nonlinear rollout, but you do a linear rollout, you basically are doing SQP. So you have all the guarantees of convergence that comes with SQP, right? And then you update your guess, and that's the same thing, right? So the thing I didn't know, and I'm stating things that are very obvious, so it's a bit embarrassing, but maybe very obvious for people who knew that basically doing SQP and doing a DDP style algorithm is the same thing, except for the line search, right? And the way we integrate the dynamics. So with the way we deal with our constraints when we do the update. In DDP, we do a nonlinear rollout, and in SQP, we do a linear update. And the question is that what's best? So at SQP, I have at least guarantees, but some people would say, yeah, but if you satisfy nonlinear dynamic, it's going to work better. So we tried that. So let me first summarize what I said, right? LQR is just a smart way to solve a tridiagonal KKT system. It's not new. Actually, if you read papers from Pertsekas or Wright, they already show that, and they already derive SQPs to solve nonlinear optimization problems. That is just we didn't know, I don't know, nobody implemented that in robotics, and turns out that you should do, that's exactly what we should do, right? So this LQR trick, you can use it for any KKT matrix that has the right structure. So basically you can tap into the whole optimization literature and just make things fast by using that. So there's no more advantage of doing DDP. And then if you look at we can start comparing all of the algorithms that we publish in robotics, right? Because now we have a common framework to compare those things. We understand what's going on. And so, for example, if you look at the feasible DDP, which is what is implemented in Crocodile, which is this very well-known software package to do a nonlinear MPC, it's basically an SQP with a nonlinear rollout. And if you look at the work of Griff-Thaler, which was done 7 years ago, right? They proposed a multiple shooting DDP style thing. They literally do a normal SQP. I don't know at the time if they knew actually that was the case, because they didn't extend it to nonlinear constraints, but so this I don't know. I haven't asked them. And then once you understand that, you can just tap into the literature. So we compared the linear versus nonlinear rollout, right? So we compared for many different examples in the Crocodile library, DDP, so FDDP with different types of line search, and a normal SQP, and a normal DDP with which is let's say the vanilla DDP implementation. And you see that if you do an SQP with a linear rollout, you basically beat everything, right? This is actually the most robust way of doing things for all the examples that we've tried. So this really gives you, so what we're showing is the percentage of problems solved as a function of the number of maximum iterations that you do to solve the problem. So you see that this actually works really, really well. And what we did is nothing new. We just implemented the textbook algorithm using this KKT trick to be fast, to be as fast, basically, as all the DDP style approaches. But now you can add constraints. So now you can add a constraint, and basically you have an SQP algorithm that is exactly the same. When you solve your QP, basically you add your inequality constraints. And so here you have to be a bit careful to not break the structure of your KKT matrix. But basically what we did, we re-implemented the SQP, which is a famous QP solver, with the tridiagonal trick I just described. And now we have, I think, one of the fastest solver that includes constraints to do MPC, which is nice because now you can actually literally just put this into your robot and you can add arbitrary constraints. So here's an example with it. So it's kind of a stupid example, but we put constraints in the end-effector space. So it's really nonlinear, right? We use the full dynamics of the robot, and we do MPC at 500 Hertz. And then we start to add constraints. We say, okay, you're not allowed to go below that. And then on the fly, the robot can adapt its behavior, right? And can guarantee that you will satisfy those constraints. And then you're going to add another constraint, and now you're not allowed to go on this side. And then on the fly, right, the robot will adapt. And then you can start to add arbitrary constraints on your robot. And then you can do really this nonlinear MPC with nonlinear inequality constraints at 500 Hertz. So here it's really exact mapping from measurement, MPC, torques, and nothing else, right? So there's nothing in between. And this actually works really well. And then you can start to do other things, right? So you can start. So for example, you force here that's an example where you force the system to be on the line, vertical line, right, going up and down for the end effector, and then you can start, abusing the robot, and then the robot will always try to satisfy these constraints. So you will get this kind of behavior, which I think is not trivial to get online, but you can actually do that by doing this solve. So if you're interested, the code is available online. It's integrated in Crocodile, so you can just conda install the code, and it's working. It's really an SQP solver with the trick is that we have we have a special QP solver that use this trick. It's a variation around the OSQP, and but you can use any type of QP solver that you will adapt with this this KKT trick. And probably you can even have much faster QP solvers, right? Because QP is already 10 years old, so you can probably do much better with more modern QP solvers. So, so far, conclusion, well, it's exciting. We do high frequency nonlinear MPC with arbitrary constraints, which I think that's not something we're able to do up to a few months ago. It's not at that speed, right? With this kind of robustness. At the same time, it's kind of embarrassing. Because we've done nothing really new. We just basically read old papers and implemented things that were known. And maybe I said this to myself, but maybe I want to convince you as well. Let's stop inventing algorithms. Let's try to know what people do in fields where actually they know what they're talking about when they talk about optimization. And maybe we can save a lot of time, right? Because we could have implemented that 10 years ago. The only thing is that we needed the QP solver is based on the DMM, and you cannot really do that on any type of QP solver. So you have to be a bit smart in how you cannot just implement a vanilla SQP. You have to do a few things on how you solve your QP problem to be able to use the trick I described. But it's nothing crazy, right? Once you understand these connections, these problems become much simpler. So that's So maybe for a model-based community. Optimization. Let's let's stop reinventing the wheel and pretending robotics is different from the rest, right? It's not. So we're done. So we're going back to that. So for the last time, I'd like to show you a few maybe at least fully novel things. So I'm interested very much into starting to integrate completely optimization and MPC with learning, right? And to really get the best of both worlds. And so I want to show you two things that we do. We do a lot of other things, but I want two things to illustrate a bit what I think is maybe a route. First is how you can use learning to plan contacts, and you basically use a mixture of optimization, optimal control, and learning. And the other thing is how you can use learning to learn cost functions that can include arbitrary sensory feedback. So now we can start to use vision into MPC in a way that maybe I find interesting. Sorry, that was the wrong slide. Okay, so learning to plan contacts. So the idea is that I want to plan contacts, and I want to leverage learning to speed things up, and I want to use I'm going to use optimal control to generate data, to do the learning to speed things up. So the problem is this way. I want to move a cube, right, from A to B along a given trajectory, right? So there's some dynamics. Maybe the cube is on the object is on the table. There's some friction. There's some contact. I want to decide where and when I create contacts, what kind of forces I apply, and what kind of trajectories I need to do in terms of forces and sequence of contacts, such that I can do actually this task, right? That's a very stereotypical manipulation problem. And so the problem is to find at each time step, right, the contact locations, timing, and deal with the environment and the finger contact forces. So assuming that I have a model of all of that. So the problem is the same, right? If you would imagine you have a leg robot, right? So that's the same problem. You want to find contacts to move a robot from it. So the idea, what we started to do is say, well, let's again use what people have been very good at doing in RL, which is tree search, right? You can start to do tree search, and basically to speed up the tree search. So here we use multi-modal tree search is to start learning how to branch, how to go through the branch, right? Learning how to explore branches, so you can do that really quickly. So if you do multi-modal tree search, right, you randomly explore a tree and you bias the exploration based on some learned value function and policy. So you decide which branch is the most likely that you should take. And then, so you can search for sequence of contacts by doing that. But the only thing is that for to know if a transition is feasible, you need to solve an optimal control problem, because you need to solve to know if it's dynamically feasible, right? So you have to solve an optimal control problem that tells you if there exist forces that are within friction cones and things like that, that allows you to go from one contact sequence to one contact setup to another contact setup, right? So the way we do that, you can use so every transition that is a contact choice. So either you create a contact or not, or remove a contact, or do nothing between the object and the robots or the environment. This as an optimal control problem, the structure optimization problem that you need to solve. And then if this is doable, right, this is something you can do, and then you can go down the tree. Sorry. So the idea is to use our fast solvers that we have, or versions of that, to start generating data between contact transitions. And basically the solver tells you if there's a solution to the solver, basically you know whether or not the problem is feasible. So you have a 0-1 answer, right? If I don't find a solution, the problem is not feasible, so that's not a good transition. If I have an answer, then the problem is feasible and it's a good transition. In addition to that, I have a cost that tells me what would be the cost of doing that, right? And this cost, I can use that to train a value, as a proxy for a value function, right? To learn how what is a good idea. A low cost is a better transition than a high cost, right? Because it means it's going to be easier to do. So we use this data to train a dynamic feasibility classifier. So this is a classifier that will tell you if you take a branch, so a contact transition, is it going to lead to a feasible optimization problem or not? And so you can train that. And then when you have a classifier, it's really easy to evaluate. And then you learn a policy value network, which is going to tell you basically what the important part, right, is the value to the cost that you get out. Let's say this is going to be a low cost, so probably it's a better transition than another one. And once you have that, then you can do online MCTS by using what you've learned. And then so offline you use an optimal control to train data. Then you train your networks, right? Your classifier and your policy value network. And then online, when you do MCTS, you just have to evaluate your network, and you be very, very fast in evaluating different contact sequences. So you can find relatively long sequences of contacts very quickly. And here we only had to train with very small sequences of contact to train the networks, right? And so we get a very, very high speed up for the tree search. And if you compare, for example, with mixed integer approaches for this kind of contact sequencing, here we're interested in dynamically feasible constraints, right? We don't look at static stability, we really look at dynamic stability, so friction cone constraints and things like that. If you do MCTS, so there's two versions, the version to compare the different versions, but the RMCTS and the one in the middle, you see that in terms of the mean time for long sequences, basically you beat by orders of magnitude any mixed integer type of implementation. But also we can deal with very long sequences. So this is the length of the sequence, right? So, we define in the paper like different types of long sequences of manipulation. And for long sequences, the mixed integer just blows up, so you cannot find solutions anymore. While we can do things in seconds, right? So it's really, really, really fast. So we planned, for example, here's an example. We have a cube. So we know that there's friction with the table. You have a cube and you want to rotate the cube. And you want to rotate the cube 180 degrees. So you need to create contact, do this, and then you need to do it again. So you need to find actually this sequence. And so we on left, this is what you plan. And on the right, that's the execution on the robot. So it's just also to convince you that we can plan things with the model and things like that, but it actually works. if you execute it on the robot, right? So you can do different things. Another one that I think is actually not so easy. If you want to actually be able to execute that on the robot, given the bad model and all these things, you can actually plan what kind of contact and force that you need to apply such that you can actually balance a cube. So you can do that in a second, right? You can plan this thing and then execute it on the robot. So we're getting close to interactive real-time rates for planning contacts using our models, especially leveraging the fact that we can learn things offline in advance. And maybe the last thing is so we can use optimization to speed up to generate data for learning, and then we can use learning to speed up planning, right? So that was what I showed you before. Now what we can do is that I would like to use learning to learn cost functions, and I would like to do that to include multimodal sensing into my MPC. So using MPC, I write down the cost function by hand, right? And my cost function is a function of the states. So state space of the system, which typically is the states of the robot, so position, velocity, maybe some forces, depending how I write this thing. But it's not very obvious to add vision or to do, say, I want to track an object and things like that without adding extra things, right? So the typical thing I have is that I have a state estimate, right? Position, velocity. Then I have a cost function that I've done by hand. Then I have a nonlinear cost for the whole sequence of actions that I want to do, right? So a nonlinear cost over time. Then I have my nonlinear MPC, and then I solve it, and then I have a control command that I execute, right? And then I do it again. So two things. What if I could approximate my nonlinear control using some multimodal perception for the cost of linear MPC? So basically say, this is what I want to do. I want to not have my state estimate. I want to use whatever sensors that I have. Then I want to maybe learn a cost function that is based on that. So at every instant of time, I will measure my state, my sensors. I will use the input of my sensors, so my cameras and everything, put this into my network. And the output will be the output of the network would be a cost function. That is a cost over n steps, right, of a quadratic cost. And since I do that at every iteration, right, at every control cycle, in principle, I can approximate any nonlinear problem that I care about, right? So then what I can do is that I will put this into a linear MPC thing, because now I use online a linear approximation of everything. So now I have a linear MPC in the sense that I will have a linear dynamics. Here we use an integrator. We're currently working with the full dynamics and things like that, but that's not what we have. So here's purely kinematics. And you can add torque constraints by using inverse dynamics, right? So here we can add position, velocity constraints, but then in principle, the idea would be to extend that to nonlinear problems. So how do we do that? How do you actually learn these cost functions that you can approximate any problem that you might care? And think about a problem that is not obvious to say. So if I have let's say I have an object that I want to track. So the input is images, right? And I would like to find a cost function that will map, and maybe there's an obstacle, and I want to find cost functions that allows me to track an object that is moving around while avoiding the obstacle. So that's a toy problem, right? But that's why we wanted to see if we could do that. And now the idea would be to extend. So when we train, we have a high level cost that is going to say we're going to use our current setup for the neural net, the current vision to output a cost function, solve the linear MPC, have a trajectory, then and see how close we go to the goal and how much we go into an obstacle and things like that. And based on that, so that's a task, right? Our task is going to be how close we go to the goal, and the X star basically is the solution to my MPC problem that is given by the cost provided by the neural net. Once I have that, since I know how far I was, I have a supervising signal, right? So then I can take a derivative of that. So I can take the derivatives through my MPC all the way back to the neural net, to the gradient descent on the neural net. And then if I do that iteratively, I will learn a cost function that will actually get my robot my system to go to follow my object. So it will find a cost such that the output of the MPC is taking me to the object that I care about, right? Implicitly. So if you do that, so right, now you can just do normal training. The trick is that you can take derivatives of your optimizer. Now we can also take derivatives of the nonlinear solvers that I showed you before. So that's what we're looking at as well. But now we use linear MPC. So you basically take the derivative of the QP, and then you backpropagate all the way to do the gradient descent on your neural net. So you have two loops: one loop that solves the MPC, and one loop that does gradient descent to learn the cost function. And so once you've done that, you've learned a cost function, and then you can at this time you just do linear MPC with a cost that is changing at every instant of time based on your sensors. So your sensors, they can be in principle anything, right? So what we did here, so the way we did it, so here I have to explain a bit. So in my lab, we don't know anything about vision. So we pre-trained an encoder that can detect the location of the object. And then from that, we feed that into the learning of the cost function that learns basically how to follow the objects and then go around the obstacle and things like that. Obviously, if you're smarter than us in terms of how you do vision, you should be able to do something better than that. But that's just to show the proof of concept that we can learn this cost function. So what happens here is that the only input is the vision, right, and the state of the robot, so position, velocity. This gives a cost function at every instant of time. So here it's running at 5 Hertz because it's the speed at which we evaluate the neural net for the vision system. We solve a QP, which is the MPC. So we get the cost function, we solve the QP, we get the desired trajectory. Here, since as I said, we use a double integrator for the kinematics. We run through inverse dynamics, and then we run the trajectory. We do inverse dynamics at 1 kilohertz until we go enough of the trajectory so that we can get an update at 5 Hertz, right? So that's the idea. So this part is not running at the kilohertz because at first we don't do the vision at the kilohertz. We could if we could do the vision at the kilohertz, but that's not what we do. And that's what happens. So now I have a system that is doing MPC with constraints. So here the constraints are on position, velocity. That has learned how to avoid the obstacle, which is a non-convex constraint, right? But it's in the cost function. That's been learned, and they can attract an arbitrary object. So I think that's one way. At least this idea of putting a lot of sensing into the cost function is maybe one way to go around the fact that MPC is not very good at dealing with sensing. At least we don't have a very good formal way of doing that. Maybe that's one way of doing that. Now we can imagine having a different cost function we can decide combining that do different types of tasks that are purely sensor driven, and we can get all the benefits of dealing with constraints. And then we can get all the benefits of being able to use learning to deal with sensing. Obviously, there's still a lot of work to do. That's just a proof of concept, but I think it's maybe one way of doing interesting things. Okay, so I've been talking for a bit, so I'm done. I think we can. So first, I hope I convince you. Maybe I said things that were obvious to you, and if it was obvious to you, that's great because you're better than me on these things. But if it was not, obviously, maybe I'll convince you that we can use textbook. We should look at textbooks because that's where everything is there, and there's no need to reinvent things until we have actually tried things that have already been proposed. Maybe it's okay if we don't publish so many papers, but at least we can do things that work and are robust and mature. So I think I would really, at least it's an advice I give myself, but maybe it's helpful for you as well. So we can really benefit from what is mature in optimization. I think the way we should go, and I think maybe that's the way we should have a discussion now. I think we should really move towards have learning everywhere but don't lose the cool optimization that we know how to do really well. And how do we do that? I think is open. So there's a lot of things to do. I showed you a couple examples of ideas. It doesn't mean that's the end of the story, but I think we should use our optimization, our simulators to generate data to reduce computational complexity, and then use learning to really speed up things, right? And pre-compute and memorize a lot of things. There's a way to include multimodal sensing. So I think learning is the way to go, right? If you want to use multimodal sensing that is really complicated, and especially if you add vision. So I showed you one way of doing that with a nonlinear optimization. There's probably other ways. So I think that's where we can do a lot of things there. I think it's interesting to get rid of finding cost functions because it's annoying. It's annoying in RL, it's annoying in MPC. So we need to get rid of that. And there's a lot of other things we should do, right? We can learn policies and value functions. I would love to see an algorithm that combines all the benefits of both doing RL and with simulators and doing a nonlinear optimization. I think we don't have that yet. I think RL algorithms are very efficient, but they are theoretically a disaster. So there's a lot of work to do there. And probably our optimization flavor is one way to do that. And we need to start using real data and demonstrations and things like that, which we don't do very well yet. But I think it's exciting because there's a lot of work to do. On that, thank you so much for listening to me. And hopefully that was interesting and love to discuss. Thank you.
Yeah, thanks a lot to Ludovic for the nice talk. I think it's now time for questions. If you want to ask a question, just raise your hand or open the mic and ask a question, or you can do it by chat. I can start with a question as long as we wait for other questions. So I really like the combination of Monte Carlo tree search and model predictive control. It's very cool. So I have a question. Once you learn, so if understood well, you're learning just the contact sequence, right? And then when you apply it online, you have like a model-based controller behind to how to say, to implement the sequence that you learned. How does it work? Because you said that you're using the trajectory optimization to find the good paths. And then you learn this classifier, which is cool. And then how do you use it? I mean, so Monte Carlo tree sets, what are the actions of the Monte Carlo tree sets?
Okay.
It's just the sequence of the contacts, or is the
actually, so that's the thing, right? So I guess I didn't explain it very well. So for MCTS, it's a discrete. So MCTS is to do research, so it's for discrete problems, right? So you search sequences of contact. You search a sequence of contact, but once you have a sequence of contact, you need to test if there's a forces you can apply that are visible that will satisfy that, right? So then you solved your trajectory optimization problem. So if you want to do MCTS, you need to evaluate a lot of these things online. So it's too expensive to solve this optimization problem online. So what we do is that we learn a classifier that tells me whether a sequence of contact will lead to a feasible problem or not. So what I learn is this classifier. So and then the second thing is that I learn a value function that tells me what would be the cost of the optimization problem. Online, I find a sequence of contact and then I solve one instance of optimization problem, which I can do online, and then I execute that.
Yeah, that's cool. Okay. Now I got it. Okay, that was a bit unclear. How do you do it there? Do you use the model-based control or not? But now it's clear. Thanks.
And maybe the one thing, right? Online, I search. So online, there's planning. So I'm searching for the contact. I didn't learn them before, right?
Yeah, it's similar to AlphaGo, right? So there's
that's exactly that. Yeah, that's AlphaGo for contacts.
Yeah. Okay. Pat, you can ask a question.
Yeah. Thanks for the great talk, Ludovic. I particularly enjoyed the more mathematical nature of it, and I guess my question is related to maybe the next step in that would have been cool to see. So the trick of using the operator splitting so that you don't disrupt the tridiagonal structure when you add the additional costs. Is that the key? Because I guess when I've thought about this before, it seemed like you add the constraints and you destroy the structure, and then I was sad and go home. Can you give us a little more insight into that?
So here, because that's a very good point. So if I wanted to go into that, I needed 5 more slides, and I decided that I would bore everyone with that. But that I see that you already thought about that. So no. So the thing is that once you start adding inequality constraints, right, you will have your the tridiagonal structure that I showed is the same, except that what happens is that the G matrix that you will the G and M matrices, they lose some of the zeros. So when I want to compute the explicit inverse of the G bar thing, that it is LQR, is going to be different, and I don't know how to do that efficiently. So then then basically what I will have to invert the size of G bar is a number of controls, and then you would sorry. In the trick, what I need to invert here is the only thing that I need to invert is something that looks like that, which is the size of the number of controls, right? But if I need to invert G bar, what I need to invert is something that is bigger, because it's going to add here I'm going to have the constraints if I add constraints. So basically, the complexity is going to grow cubic in the number of constraints if I do that. This way, if I do that without using any operator splitting method, right? So
but still using the Thomas algorithm, you would still get linear performance.
You will get linear. You will get linear time performance, but you will not get. You will get. The cubic part will not just be cubic in the number of controls. It would be cubic in the number of constraints as well. So if you have, so basically I think it's going to. Okay, normally it's going to be cubic in the number of I don't want to say something wrong. I have to write it down because I don't remember. But normally you're going to have basically you're going to double the number of states, the size of your matrices at least. So basically you're going to lose a factor 8 in the complexity of the inversion of every matrix. And that's what you see. Some people have implemented this kind of augmented Lagrangian DDP style thing, and they have a factor 8 that they cannot get rid of because of that. With the SQP that I write here, let me just go here. What we do is that we use we linearize and qualitize the qualitize the cost, linearize the dynamics and the constraints, right? We also take linear approximation of the constraints. When you solve the QP, what you have is that once you've done that, you got rid of your Lagrange multipliers in the nonlinear problem, and you put them into your quadratic program. So you got rid of a lot of you got rid of this factor 8 basically by doing that. And then what happens is that when you do a SQP style thing is that you can split the problem into prox operators projection operators for the constraints, and then for non-equality constraints, and then you would have you can solve when you do this ADMM, you split the problem into several sub-problems, right? One of the sub-problem is the linear dynamics equality constraints and the quadratic cost. And the other problems are the inequality constraints. So basically when you do that in this specific flavor is that you do LQR, literally LQR plus prox. And so that's it. And then you do use the scheduling of SQP, so it's really efficient. But that's how you retain. So the linear complexity is the same, but you also retain the small matrix inversion in every step. I hope I didn't lose everyone, but yes. So the operatic splitting is important to be able to retain the small matrix inversion at every step. The linear complexity, you get it, and anyway, whatever you do, it's fine. Yeah.
Thank you.
Yeah, thanks. Actually, pretty good. I hadn't seen this, so I will have a deeper look into it. So
it's
Yuval,
in the paper. If you want, you can look at the paper.
Yeah.
It's better explained than what I did.
Yeah, I just marked it so that I can have a deeper look. So Yuval, you can ask the question now if you
let me try. Can you hear me now?
Yeah, we can hear you now.
Okay. I wanted to ask about the tree search for contacts. This, like, I can see how it would work with kind of a very hard, very sticky contacts, which are effectively, like local equality constraints. But aren't the contacts which are interesting contacts, like between fingertips and rigid or soft and soft, like these things, they may be stiff relative to other things in the system, but they're still very, very soft. You know, a contact does not appear or disappear. It comes into existence smoothly.
Well, okay. Well, it comes to existence. I mean, okay, it depends, right? If I have my robot that jumps and that lands, if I look at my sensors, there's nothing smooth about that, right? Okay.
Yeah, no,
Um,
I'm thinking about the manipulation setting.
but for
So, okay, I
manipulation,
guess
right?
for locomotion, it might make sense,
If
but
I have
in
if I have
manipulation, two things happen. First of all, the contacts are potentially, you know, if I'm thinking about fingertips or rubber or human
yeah,
fingertips, they are very soft. And the other is that the branching factors become crazy.
yeah. So MCTS is good for dealing with very crazy branching factors, right? That's why you need to learn how to search. So if you don't learn how to search, you have no chance, right? Because the branching is so insane that you have absolutely no chance. I think the way we formulate it is maybe not the right way, right? There's probably a lot of work to be done, but I think searching is important. But the branching factor is killed if you can learn which branch you need to take. So if you can learn only a few, if you can prune most of your branches ahead of time, then it's okay. Because it turns out that most of the contacts make no sense, right? The majority of the contacts you might explore are completely irrelevant. So if you can learn that, then you don't have that much to search anymore. The other thing that you're saying is completely true is that most of the robots we have are rigid. They have rigid fingers. So these things, the modeling approximations we've made are, I think, okay. If you want to go toward more dealing with deformable objects or dealing with deformable fingers and things like that, right, where it really matters, right? First, the modeling we made is not correct anymore, so you cannot use that. And probably you will have to rethink the way we search, because probably this is not the right way of searching. And for certain problems, where the model as discrete, maybe it's not discrete anymore. So maybe it doesn't make sense to, maybe you can write this as a continuous optimization problem, which actually would be great because it makes my life easier, right? Well, it depends, so no, yeah, you're absolutely right. It's going to depend on what your problem is and what you want to choose. The branching factor is that's what we attack, right? We attack the branching factor and we can deal with it. The modeling, it's going to depend on what's your robot. If your robot is soft and you deal with soft things, my modeling is not correct. So I have to do something else. Yeah.
Anybody else has something else to say? Okay, then I have another question regarding the last part where you learned the reward functions.
Yeah.
So two questions. So first, you said that you're optimizing, you're getting the gradients through the MPC.
Yeah.
So I have a more philosophical question. Why didn't you try any black box optimizations to do this, and you went to take the gradients through the MPC? This could allow you to use a more sophisticated MPC and still be able to learn the.
Yeah. So okay, so there's many reasons. Okay, so first, so there's a very practical reason. We said, oh, we have this idea, let's see if it works. So if you want to see if it works, you're going to try to set up the simplest thing you can do. And taking derivative of QP is something that is very easy to do. And then you can do gradient descent, and then you can focus on what really matters, which for us, we had no idea how to deal with vision, right? We spend a lot of time doing stupid things. So you put your effort there and you say, okay, the optimization, I take something I know that is easy and I don't have to deal with it. So that's one reason, right? We are currently, so Avadesh, which is a student who is actually working on that, is currently looking into the nonlinear solver that I showed you. You can take derivative of that, so it's fine. We know how to do that. It's just at the time we didn't have the software that could do that quickly. And then you can still use a similar idea. But yeah, for the proof of concept, we tried the simple thing, right? That's one way. The other thing is a black box optimization. So each time you have an optimization problem, right, you can do whatever optimization solver is fine, right? I like gradients because they tend to converge reasonably fast. If I use a non-gradient based method, then I have less. I don't know. I have less control on how it converges. But it could work, right? I mean, there's no reason why they would find a solution. Gradients are nice. I mean, stochastic gradient descent for neural nets works really well. So why would I do something else?
I'm not disagreeing. Just wanted to see because I have seen, for example, some works that try to combine to learn rewards for for simple models for locomotion, for example, and they're using, for example, SIMIS and stuff like that. That was the question.
No,
basically to approximate RL with a black box optimization or something like this.
No, it makes total sense. I think it makes a lot of sense. I think, yeah, absolutely. If it works better for whatever setup, you should absolutely do that. Yeah.
Okay, cool. So is there any other question from the audience? I think there's no other questions. So let me thank you again for the great talk. I really enjoyed it.
Yeah.
It was very nice insights, and I think it went well because you were worried in the beginning. It went very well, so it's good.
Okay, so you're not starting to put it online. That was your. Okay.
Okay, thanks a lot.
All right, thank you so much. Thanks everyone, and
thanks everyone for the participation. Yeah.
Bye.